Hello, everyone. We are from Baidu Security and have long been committed to research in AI security. Today, we're going to share a new research topic about Wi-Fi mesh. In this topic, you could get the concepts, principles of Wi-Fi mesh. Besides, you could learn the attack surfaces of this scene and get some high-risk security vulnerabilities in the real world. Let me introduce our four speakers. Me, Lewei, is a security researcher of Baidu Security. He's interested in bug hunting and fuzzing. He recently focuses on IoT mobile security and wireless security. He reported several security issues to Google, Oracle, Android vendors such as MediaTek, Xiaomi, Oppo. Dongxiang is a security researcher of Baidu Security. Recently, he focuses on IoT security and wireless security. Zhang is a security researcher of Baidu Security. He's interested in reverse engineering and bug hunting. Recently, he focuses on IoT security and fuzzing stuff. He reported several issues to Apple, Google, Microsoft. Wang is a security researcher of Baidu Security. He focuses on automated vulnerability detection technology, such as dynamic symbolic execution and fuzzing. Now he engages in fuzzing of AI frameworks and Wi-Fi protocol. We'll share our research about Wi-Fi mesh in 5 parts. In the first part, we'll introduce the background of Wi-Fi mesh. We'll also introduce the main role in this topic, EasyMesh, which is a certification developed by Wi-Fi aliens. We'll introduce the history of EasyMesh. In the second part, we'll show the progress of EasyMesh. We'll introduce the architecture of EasyMesh. Also, we show the attack surfaces in the whole progress. In the third part, we'll introduce a tool named MeshFuzzer and share our design idea and show how this tool could detect security issues automatically in Wi-Fi mesh. In the fourth part, we'll introduce the security issues we found in MediaTek MT7915 chipset with MeshFuzzer. In the last part, we'll put forward our suggestions and direct our future research. What is Wi-Fi mesh? First, the mesh is a common technology of network build. By using mesh, several access points could get together and serve as the same network. Compared to the traditional Wi-Fi network build technology, mesh has the advantages of being more flexible, more reliable, faster. It also has the great features of self-organization, self-management, and self-healing. So Wi-Fi mesh plays a significant role in the future scene of Internet of Everything. So what is EasyMesh? EasyMesh is a standard certification developed by Wi-Fi aliens. EasyMesh has gone through 3 developing stages since 2018. In 2018, the vendors developed mesh in their devices themselves. So the devices from different vendors could not get in touch by Wi-Fi mesh. There is an urgent request for standard protocol to help vendors to get together. So in 2019, Wi-Fi aliens designed an EasyMesh R1, which introduces onboarding and auto-config. It also claims to use 1905.1a control protocol to implement most of the functions of Wi-Fi mesh network control. In 2020, Wi-Fi aliens upgrade the EasyMesh from R1 to R2. In this version, EasyMesh gets more features. It is worth mentioning that the EasyMesh introduces several security features, such as the integrity and authorization of message. Up to now, dozens of vendors have got the certification of the EasyMesh, such as MediaTek, Huawei, ZTE, and so on. So let us introduce the architecture of EasyMesh. Here, there are 2 key links and 2 key roles. First, the two key links. The front hall link is the link displayed in our normal life, which our smartphone could find it automatically and get in touch with the internet. Second, the back hall link is the link that could not be searched in the normal world. It is a hide SSID. It is designed for mesh networks only. Next, let us look at the two key roles in Wi-Fi mesh. The controller is the commander of mesh network. It could send controlling actions to other devices in mesh network. So by sending some specific commands, the mesh network could reach the goal of self-organization, self-management, self-healing. The agent is the executor of the mesh network. It could parse the command from controller to finish task of the network controlling and feedback the results to the controller accurately. So we will introduce the progress of network build. The whole progress of network build could be assembled as two parts: onboarding, discovery, and configuration. First, we'll introduce onboarding, which will help a device to join a mesh network. Here, we call the device which want to join the mesh network an enrollee device. The onboarding progress is implemented by a protocol named 1905 push-button configuration. The 1905 push-button configuration protocol has three features. Feature 1 is the device needs a push button in the real world. Feature 2 is the 1905 PPC is based on Wi-Fi Protect setup. Feature 3 is the 1905 PPC is based the type length value. So we could see from the picture follows, 1905 PPC designs multi-AP extension in the payload, which means the enrollee device could get backhaul SSID and password through 1905 PPC. The whole progress is shown in the right picture. First, the two devices need a push button. After that, the two devices are in the state of network build. Next, the enrollee device follows 1905 PPC and goes through M1 to M8 and gets the backhaul SSID and password from existing agent. Finally, the enrollee device could get in touch backhaul SSID and join the mesh network successfully. Here, the progress of onboarding is finished. Next, we'll introduce the progress of discovery and configuration. By finishing onboarding, the enrollee device needs to find a controller to get configured with the mesh network by using the 1905 controlling protocol. First, the enrollee device sends a 1905 packet to figure out if there is a controller device existing in the mesh network. The type of the 1905 packet is AP auto configuration search. If there is a controller existing in the mesh network, the controller will respond an AP auto configuration response to the enrollee device. So the enrollee device finds the controller successfully and the progress of discovery finish. Next, the controller gonna configure the enrollee device. It will pass some significant configuration parameters to enrollee device, such as password, access control list, channel of communication. This is implemented by the type of AP auto configuration Wi-Fi sample configuration, as shown in the picture right hand. Just the two progress, M1 and M2. At last, the enrollee device gets configured and transferred to the new role agent and will act as a member of the mesh network. Here, the whole progress of network build complete. We have shared the whole progress of the network build. Next, let us look at the network control. The management and maintenance action are really important parts of mesh network. It is implemented by the protocol of IEEE 1905.1a. The IEEE 1905.1a is a protocol between the physical layer and the network layer. It defines the controlling technology in home network, whether wireless or wired. In the mesh scene, IEEE 1905.1a is the payload, and EasyMesh describes several controlling protocols, such as device finding, device configuration, and device management. The whole protocol is based type length value. Here, we list some of the protocols in EasyMesh and choose the type multi-AP policy config request as an example. The multi-AP policy config means some strategies in steering policy of mesh network. The command is 8003. We can know the type is 0x89 and the length is 21. The payload are shown in the picture left hand, so each packet in mesh network control is just like this. So we have shown the principles of mesh network build and control. So what are the attack surfaces? The two basic attack surfaces are network build and network control. The two key protocols are 1905 push button configuration and IEEE 1905.1a control protocol. And the protocols are based type length values, so they may have memory corruption and parsing TRV block and are very suitable for fuzzing test. Here, look at the attack surface of mesh network build. First, an attacker disguises a malicious enrollee device to attack the existing agent. It could send the malformed packet in the progress M1, M3, M5, M7 of 1905 PPC, could trigger the security issues in the TRV parsing in existing agent. Next, an attacker could disguise a malicious existing agent to attack the enrollee device. It could respond to malformed package M2, M4, M6, M8 of 1905 PPC, could trigger the security issues in the TRV parsing enrollee device. Here, let us look at the attack surface of network control. An attacker should join mesh network first and disguise malicious controller and existing agent to send a malformed packet. This may trigger the security issues of the controller and existing agent in TRV parsing. The picture right hand shows we use the command AP auto configuration WSC message. We fill the length of SSID to 0xFF, which is 64 bytes longest in normal. Also, we fulfill 0xFF to the payload of SSID. From the packet we capture, you could say our payload X0xFF fulfills the packet. This is unusual to a normal device. So let us introduce our automatic bug hunting tools. We name it MeshFuzzer. We will introduce it as 4 parts. First, the architecture of MeshFuzzer. Second, the strategies of mutation of type length value. Third, how we fuzz network build. Last, how we fuzz network control. And there are 2 subsystems in our MeshFuzzer, 1905 PPC fuzzing and IEEE 1905.1a fuzzing. The top half part is our design of 1905 PPC fuzzing subsystem. We choose the WPS data between devices in the real world as our original data. The original data will pass through our TLV mutation subsystem and use the 802.1 packet publisher to send packets. By the way, our monitoring model will get in touch with the UART port of the device to capture the crash logs. The second half part is our design of 1905.1a fuzzing subsystem. We implement most of the control protocol described in EasyMesh. Also, the original data will pass through the TLV mutation subsystem and use the 1905 packet publisher to send packets. And we design a special mechanism to monitor whether the 1905 diamond is crushed or not. Due to the implementation of the target protocol is based on type length value, we could design a group of strategies to help fuzzing. First, we mutate the length field by changing the length to a too short value or too long value. We may trigger some memory corruption, such as a too short value could cause out-of-bound read or integer overflow. Too long value could cause out-of-bound write security issues. Second, we could change the block of TLV randomly, such as randomly add, randomly delete, and this may trigger some logical security issues, such as double free and use after free. The picture in the left hand shows the two shotguns in the real world. The picture in the right hand showed we add a TLV block randomly. We could cover most of the issues in parsing TLV in the strategies upper. Now, let us see how we fuzz the network build. About the fuzzing hardware, we choose a Ubuntu PC or Raspberry Pi 4. We also buy a USB Wi-Fi adapter to help sending their 802.1 packets. About the fuzzing software, we choose an open source tool, WP supplicant, to modify to build our fuzzer. The reason is that the WP supplicant supports the 1905 PPC protocol originally, so we could put our fuzzing strategies in several stages of 1905 PPC, and this could help us to fuzz network build stably and efficiently. As we mentioned before, there are two potential victims in network build. One of them is an existing agent. We could build the fuzzing payload with our specific tools and could cover M1, M3, M5, M7 progress. This picture right hand is the captured crash log that we triggered in M7. This is an out-of-bound write issue in which the existing agent handled the malformed packet incorrectly. Our method of the monitoring is just to pin the target existing agent and connect to UART to capture crash logs. So another victim in the network build is the enrollee device that has not joined the mesh network. We disguise a malicious existing agent to fuzz the enrollee device. To keep the enrollee device being in the state of joining mesh network, we add a script in the enrollee device, just as we shown in the picture left hand. We inject our fuzzing payload in the progress M4, M2, M4, M6, M8 successfully. The right-hand picture is the captured crash log we triggered an out-of-bound write security issues in the progress M6. Here we also use the method of the pin target device and get UART crash log. In this part, let us introduce fuzzing network control. We chose MacBook Pro as our hardware because it could support the packet sending in IEEE 1905.1a. About the software, we choose an open source PY IEEE 1905, which has implemented some of the protocols of controlling. This is a great piece of news for us. It means we just developed some of the protocols of EasyMesh and add our mutation strategies. So we could fuzz network control easily. In the monitoring part, a special mention we need to figure out if the module handling the IEEE 1905.1a packet is a diamond. So we could not capture the crash in the UART port, and also we could not send a pin message to check the diamond is alive or not. So we use a 1905 topology query message in the EasyMesh. which is described as a message to detect each other in 1905 diamonds. We could easily know the state of 190 diamond is alive or not. So when we post a fuzzing payload, our fuzzer will post a package of 1905 topology queries. If got feedback, it means the 1905 diamond works normally. If not, there may have been some problems in the 1905 diamond. We will save the fuzzing payload and wait for the diamond to restart. Next, my partner Dongxiang will show you the security issues found by MeshFuzzer in the real world.
Hello everyone. Next, I will introduce some security vulnerabilities we discovered during the security audit of the MT7915 chip. Those vulnerabilities can be roughly divided into two categories in terms of causes. Firstly, memory corruption vulnerabilities, mainly due to the lack of validation when processing TLV packets. Vendors often introduce such vulnerabilities when implementing Wi-Fi mesh protocol stacks, such as stack overflow and heap overflow. Secondly, vulnerabilities that violate security principles, mainly due to the violation of safety principles defined in the EasyMesh standard. For example, the backhaul link and the fronthaul link need to be isolated in a Wi-Fi mesh network. We chose the MediaTek MT7915 chip as our research target for Wi-Fi mesh, mainly based on the following three reasons. Firstly, the MT7915 is the world's first single chip Wi-Fi 6 with 1 Plus and Bluetooth 5 combo solution. The chip integrates a dedicated RF receiver with zero-weight DFS channel monitoring, an industry first, that brings faster, highly reliable, and easier to use connectivity. Secondly, the Wi-Fi mesh solution of MT7915 chip has obtained the EasyMesh certification of the Wi-Fi Alliance. Thirdly, MT7915 is a cost-effective Wi-Fi chip. It's adopted by many Wi-Fi 6 wireless routers. Those advantages are very beneficial to our security research. In our security audit of the Wi-Fi mesh solution of the MT7915 chip, we found some security issues, which cover the network build stage and network control stage of the Wi-Fi mesh process. A total of 19 CVEs was obtained. MediaTek had fixed all the security issues and released the corresponding patches. First of all, I will introduce two memory corruption vulnerabilities. CVE 35055 we discovered in the mesh network build stage. Attackers can use these vulnerabilities to remotely trigger out-of-bounds write in the adjacent network without knowing the Wi-Fi password. The device will join the mesh network through the 1905 push-button protocol, as can be seen from the code in the figure. After the AP received the WC packet, it directly passed the process it without validating the data packet. The trigger point of the vulnerabilities is a memory copy operation here. The target address is a 16-byte area, and the copied data and length are all passed from the WC packet. When an attacker sends a careful construct WC packet with an enrollee nonce greater than 16 bytes, the out-of-bounds write can be achieved. The picture on the left is a crash log triggered by this vulnerability, CVE 37566, we discovered in mesh network control stage. An attacker can use this vulnerability to remotely trigger an out-of-bounds write in an adjacent network. When the Wi-Fi mesh network is established, the AP will manage the mesh network through the 1905 protocol, as can be seen from the code in the figure. After AP receives the 1905 data packets, it directly passes and processes it without validating the data packet. The trigger point of the vulnerability is the memory copy operation here. The destination address is a 33-byte area, The copied data and length are all passed from the 1905 data packet. It has not undergone any verification. When an attacker sends a carefully constructed 1905 data packet with an SSE length greater than 33 bytes, an out-of-bounds write can be triggered. The picture on the left is the crash log by this vulnerability. Next, I will introduce a vulnerability caused by violation of security principles. In the EasyMesh standard, the Wi-Fi mesh network is divided in two links, front haul and back haul. The front haul link is used for normal network communication between the device and the AP, and the back haul link is used for transmission of mesh network management data between the APs. However, in this mesh implementation, front haul and back haul links are not strictly isolated. Common devices that send a false mesh network management messages in the front haul link will also be received and processed by the AP normally. Therefore, the attacker can pretend to be the mesh network manager as shown in the POC and send the 1905 data packets from the front haul link to block the specified device from accessing the mesh network. From the AP serial port log, it can be seen that after running the POC, when the specified device is connected to the network, the request to join the network will be ignored by the AP, causing the device to be unable to join the mesh network. For the repair of the above-mentioned vulnerabilities, we have the following suggestions. For memory corruption vulnerabilities caused by processing TLV packets, we recommend to pass the data packet completely, then check the type and length one by one, and finally process it, and discuss it when the length and type check fails. A good example is WPA supplicant. The figure shows the process of WPA supplicant processing TLV packets, which follows the process of passing and dispatch and validation and processing. For vulnerabilities caused by violation of security principles, there is a section in the EasyMesh version 3 standard that specifically describes the security capabilities of 1905 protocol. For example, to isolate backhaul and front haul link, and integrate code, which is an integrated transmission counter used by sender to prevent reply attacks, and also encrypt the 1905 protocol layer. We suggest that when implementing EasyMesh, vendors should abide by the EasyMesh standard and implement the security capabilities of the 1905 protocol. Next is a summary of the whole topic. In our research on Wi-Fi mesh, we discovered a new attack surface. Attackers can launch attacks on the devices in the mesh network during the mesh network build stage and network control stage. In this regard, we developed the MeshFuzzer, which can automatically mine the security vulnerabilities introduced by vendors when implementing EasyMesh. In practice, we found some security issues and obtained 19 CVEs in the Wi-Fi mesh solution of MT7915 chip. And we classified the vulnerabilities found and gave the corresponding repair suggestions. For future research work, we have the following plans. Firstly, use MeshFuzzer to mine the vulnerabilities of other EasyMesh vendors. Many other vendors' Wi-Fi chips have also obtained the EasyMesh certification. In the next research, we will verify whether the EasyMesh implementations of those vendors have similar problems. Secondly, extend MeshFuzzer to adapt to some vendors' unique Wi-Fi mesh solutions. Many vendors will develop their own Wi-Fi mesh solutions, such as Qualcomm's QSDK. In the next research, we will also conduct security audits on this type of Wi-Fi mesh solution. Thank you, everyone. The above is all the content we shared today.